Welcome back. In this lecture onwards, I will start a new module which is on characterization of polymers and specifically about determination of polymer molecular weight. And in this particular lecture, I plan to cover membrane osmometry, in-group analysis and dilute solution viscometry. Membrane osmometry is based on colligative properties of a solution, and from your previous knowledge you know that colligative properties of solution depend on the number of molecules. Now, when you talk about number of molecules, the molecules should be non-volatile and very dilute solution. So, colligative, the amount or the magnitude of colligative properties of a solution depend only on the number or moles of solute present in the solution. There are 4 colligative properties: elevation of solvent boiling point, depression of solvent freezing point, lowering of solvent vapor pressure and osmotic pressure of solution. Now, if you look at the data, which is a comparison of colligative properties of 1% solution of polystyrene of molecular weight about 20,000 in benzene, look at the magnitude of the changes in vapor pressure or boiling point, freezing point, osmotic pressure. Now, these are very small amount. So, these are very difficult to capture experimentally. So, there are always some error involved in these techniques. So, what I will do, for this course I will mainly talk about osmotic pressure and briefly mention about these 3 techniques after speaking about osmotic pressure method. In osmotic pressure method, in a chamber we have pure solvent one side and other side we have solution which contain solvent plus polymer, in this case polymer as a solute, and this is a semi permeable membrane, which means that this is only permeable to the solvent molecules, not the solute molecules, which is polymer in this case. Now, if you recall, the chemical potential of a component in a solution is at a particular temperature is given by standard chemical potential plus RT ln xi, this is the mole fraction, or for a ideal solution, this for ideal solution, and for a real solution we write as a activity. Now, we are talking about very dilute solution. So, we can consider this close approximation to ideal solutions, we can consider this equation. Now, for a solution the chemical potential is always less than the chemical potential of the pure solvent, because this is a fraction. So, this is a negative quantity. So, mu I t will be always less than mu I t, chemical potential of solvent in a solution, which will be less than the chemical potential of pure solvent at that particular temperature. Now, we know that to maintain or to achieve a chemical equilibrium, any component always move from one phase having higher chemical potential to a phase which is at a lower chemical potential. Hence, the solvent will try to move from pure solvent phase to a solution phase, and we call this as osmosis. As you know, this is osmosis. How long it will continue? Ideally, it should continue till all the solvents are over in this side, but in this case as more solvent comes, there is a extra pressure build up, and which is of the magnitude of this height h and the density of the solution h d into g. So, that is the height of the additional compared to this side, the pressure is more in this side. Now, we also know that d mu or chemical potential with respect to pressure at constant temperature is given by Partial molar volume, or in this case because we are talking about dilute solution, we can write the molar volume of the solvent VIM. This is a positive quantity always, hence the chemical potential will increase with increase in pressure. So, as the pressure increases, it will come at one moment, the chemical potential of solvent both the sides will be equal and equilibrium will be achieved. Now, once the equilibrium is achieved, the corresponding height, the pressure, the additional pressure is called pi or the osmotic pressure. So, osmotic pressure is the additional pressure required to maintain the equilibrium between the solvent phase. Now, we can have other types of setup where we have solvent here, solvent in this outside and solution within this separated by semi-permanent membrane. So, on equilibrium the height goes up. So, this pressure is given by HdG corresponds to pi additional, that is called osmotic pressure. So, we know osmotic pressure. Now, we have seen from our earlier classes that osmotic pressure can be expressed in this way, where m is the molecular weight of the solute, c is the concentration in mass per unit volume. Generally, when you talk about concentration, we generally talk about moles per liter or moles per volume, but because we do not know the molecular weight itself, we are trying to find out the molecular weight, we will always express this concentration in terms of mass per unit volume. So, it is basically it is a mass concentration, not mole concentration or number concentration. Please note, this is very important that for this, when you are talking about these polymer solutions and related properties, we are talking about mass per unit volume. And A2 is the second virion coefficient, which is given by this expression as we have seen earlier also, where rho 2 is the density of the polymer and V1 in the molar volume of the solvent, and chi is the polymer solvent interaction parameter, which we discussed earlier. Now, if the solution, we can express this expression, just multiply by C both side, we get this expression. Now, if the solution is very dilute, then we can ignore this second square term and c to the power cube term from the right hand side. So, we can just write this, okay, in case of very dilute solution. Now, if we consider that the osmotic pressure of a solution of a polymer is summation of the osmotic pressure generated by each polymer molecule. So, we can write the total osmotic pressure is summation of the osmotic pressure generated by individual molecule. Then we can write this expression as summation of this, and we can express Ci in terms of basically we can divide and just replace this pi with this term, and then we can express this, which means that it gives this expression, which is nothing but Mn. So, when you talk about osmotic pressure, determination of molecular weight by osmotic pressure, we will be determining the number average molecular weight, as shown by this derivation. So, instead of m, now we are putting mn and we have seen this expression. So, now we can basically plot this pi by c with several polymer solution of different concentration and then plot pi by c with respect to c, then we can basically get a straight line. If we talk about very dilute solution, then we can ignore this second order terms. So, we can just write only the A2C term, and at C is equal to 0, the intercept will give us this quantity from which we can get the Mn value. So, what we need to do? We need to basically make few solutions of known concentration, concentration means mass per volume, and measure osmotic pressure for each of these solution, and then plot pi by c with concentration, and from the intercept we can get number average molecular weight, and from the slope we can get this second variance coefficient from which we can get the polymer solvent interaction parameter as well. Now, please note that we are not calibrated this osmotic pressure measurements with any known polymer molecular weight, which means this is a absolute method of determining molecular weight, and the molecular weight in this case number average molecular weight, which we report by measuring measurement using of membrane osmometry is a absolute value of molecular weight. Now, when we talk about theta solvent, we know that theta solvent, the value of polymer solvent interaction parameter is 0.5 or half, which means in theta solvent this A2 term will be 0. So, we can just determine pi by c at any concentration, and we can use that value of pi to get directly Mn value. We do not need any extrapolation in that case, because in that case, that means in case of theta solvent, pi by c value or pi value do not depend on the concentration of, or pi by c does not depend on the concentration of the solution. So, this is the example where pi by c is plotted. So, pi by c unit is joule per kg inverse SI unit, and concentration is gram per dm cube, that is a unit. So, PMMA dissolved in 3 different solvents. This is toluene, this is acetone, and this is acetonitrile. So, in this case you see pi by c value does not depend on the concentration of the polymer solution. Hence, we can use any of this data to find out the molecular weight Mn, or if we are not using any theta solvent, then from the slope, initial slope, we can find out the A2 value, and from the intercept we can determine the Mn value. And as you can see, the more good solvent, the higher is the deviation from linearity in. So, basically when you have the solvent is good, then the additional type, the C square terms, C come, those are also come in the picture, and there is deviation from linearity, and the slope is higher when the solvent is good, because the chi value becomes less than 0.5 for good solvent, and lower the value for chi we have seen earlier, the better is the solvent quality for that polymer, hence the slope also increases. Now, we just need to keep this information in mind during membrane osmometry, that membranes for different solvents are different. For example, organic we have cellulose gel cellophane type membrane, aqueous solvent we have cellulose acetate membrane, nitrocellulose membrane, for corrosive material we have glass membrane and so on. And the membrane should be able to have a proper pore size and its distribution, and should be there be in wet condition, and dried and membrane should be discarded because the pore will not be effective in that case. Next, we will talk about briefly the other three techniques, namely vapor paper osmometry, albumetry and chiroscopy. The name, as the name suggests, vapor pressure osmometry deals with the lowering of solvent vapor pressure by a polymeric solvent. Now, generally in experiment we do not measure the vapor pressure difference. What we do, we basically maintain a solvent and a solution chamber, and the temperature is varied to keep the vapor pressure in both sides equal, and we can express this delta T by C like the pi by C. We can express similar expression where the constant term is different. Now, delta T is the temperature difference between the polymeric solution and the pure solvent in the vapor phase equilibrium with each other. So, basically the temperature difference which need to maintain to have a equilibrium between the solution phase and solvent phase. Now, Kc can be expressed this way, where delta H V is the heat of vaporization for the solvent, and this is the molar volume of the solvent, and rest of the things is explained here, and T0 is the temperature of the pure solvent. Again, C is the polymer concentration, is mass per unit volume. So, the Kc depends, value of Kc depends only on the solvent and temperature. So, in this case also we can find out Mn by determining or measuring the delta Te value for different solution having different concentration of polymer, and then by plotting delta Te by C with C we can find the Mn from the intercept and A2 from the slope, as we did for osmotic pressure. Similarly, albumetry, which deals with elevation of solvent boiling point by a polymeric solute. In this case, this T is the difference in the boiling point for the solvent and pure solvent, and rest of the treatment remains similar. In case of chiroscopy, which deals with lowering of solvent freezing point by a polymeric solute, in this case this temperature difference is the difference in the freezing point of the pure solvent and the solution. In this case only this in terms in place of delta Hv we will write delta Hm, which is the molar enthalpy of melting for pure solvent. We are talking about lowering of freezing point. So, we will use delta Hm instead of delta Hv. So, we can now use these three technique as well to find out the value of Mn and A2, and these three techniques are actually relative techniques, because to find out the value of Kc or the other K values we actually need to use a polymer of known molecular weight to get this value. Theoretically it should be absolute measurement techniques, but in practical sense to actually achieve this experiments we need to have a value of this Kc and other corresponding K terms for these two techniques, which can be only obtained using known molecular weight polymer Hence, this is a relative technique. So, we can write that ideally or theoretically or by in principle it should have been a absolute technique, but in practically these are relative techniques. Now, we need to be very careful about impurities in this measurement, because we are talking about number of molecules present in the solvents which determine the value of these properties. Hence, even if we have a small impurity that affect the mean value determined by these techniques a lot. For example, if I have a impurity of water and water mole weight fraction is so low, like it has 1% by weight, then for a Mn actual Mn of 2 lakh, it will turn out to be 1748, which that means there is a drastic change in the molecular weight determined by this any of these techniques, colligative property type measurement technique, in presence of 1 weight percent of water. Similarly, if we had 1 weight percent, because now toluene has higher molecular weight, so the number of molecules will be less, hence the error is comparatively less compared to the water. So, just you need to remember that while using these colligative property techniques, measurement techniques, we must be very careful about the impurities present in the solution. Next technique, we will talk about N group analysis. Now, this also gives us number average molecular weight, and the basis of this measurement is the determination of number of moles of N group for a particular type of N group in a given mass of polymer. So, basically we know how much polymer by weight we can take in a solution, and if we know what is the number of moles of N's present in this polymer sample, then we can get the value of Mn, provided we know that number of N's present in a polymer chain. So, it can be used to determine the polymer sample if the substance or the polymer contain quantifiable N group. Some cases if we have N groups which we cannot determine or we can quantify, then it is not possible. So, we need to have any mechanism or any characterizing technique by which we can quantify the number of moles of N groups present. So, that may require that functional groups which and basically other functional groups which interfere with the N group analysis either must be absent or their effect must be basically accounted. So, if we have a N group and there is another group present in the middle, in the backbone, not in the end, which interfered in the N group analysis, then it is very difficult for us to determine unless we take care of the interfere, which is very difficult technique to do. And the concentration of N group must be sufficient so that accurate measurement is possible, accurate quantitative measurement is possible. And the number of such group or N groups per molecule, per polymer molecule is known beforehand. So, we should know that whether it is a linear polymer having 2 ends or is the branch polymer having more than 2 ends. So, that we must know to find out the polymer molecular weight. And it is also restricted because as we increase the molecular weight, the number of ends for a given weight of sample comes down, hence the measurements or quantification of these ends also become difficult. Hence, this analysis is restricted to low molecular weight polymers with well defined structure and distinguishable N groups, and upper limit is dependent on the sensitivity of the techniques which we are using, and typically it is done for 10,000 to 15,000 molecular weight. Generally, these are the techniques which which are used for quantifying the N groups. If we have acid groups, alcohol groups or base groups type like that, we can use titration technique to quantify the number of moles present in the N group, and we can do like elemental analysis, and we can do radioactive labeling, or we can use some other spectroscopic techniques which can determine the concentration or number of moles of N groups present in that particular sample. And the concentration of N groups varies inversely with molecular weight. So, N group methods tend to become unreliable for higher molecular weight, as I explained before. So, upper limit is 50,000, but preferred range is 5,000 to 10,000. And as I said, because in case of branch polymer we do not know how many N's are there per polymer molecules, sometimes very difficult to know. So, it is not very applicable for branch molecule. And this actually, if you can know how many N groups are present and what are the types of N group, then that actually help us to find out the mechanism of initiation and termination reaction for chain polymerization. To find out the molecular weight, we need to find out Me, which is equivalent molecular weight of the polymer, and sometimes called equivalent weight, is the mass of polymer per mole of N groups. And once that, which means Me, this is the total mass, Ni is the number of moles of polymer chain, and this is the molecular weight. So, this multiplication gives the total weight, and this gives us total number of N's. The Ni is the number of polymer chains and F is the number of moles per polymer chain. So, F multiplied by Ni will give us total number of N's. Hence, this is the average mass of polymer per mole of N groups. And we know Mn is given by this expression, hence Mn will be given by F into Me. Me we can determine quantitatively by these techniques which I showed in the last page, and if we know the F value, which is the number of N groups per polymer molecule, then we can find out Mn. I will just give you an example of determining of N group analysis by NMR techniques. If you are not aware of NMR technique, it is fine. You should know that NMR can be used to identify chemically organic compounds or polymeric compounds, and in this case proton NMR. So, NMR for each protons present which are different chemical environment will produce different signal, and the intensity of that signal will be proportional to the number of such proton present in the molecule. So, in this particular case I have poly N isopropyl acrylamide polymer, and we need to find out exclusive protons which are present at the end and somewhere in the repeating unit. So, in this case the end CH3, this has a long chain C12H25. So, at the end it will be CH3. Now, that peaks come here and it has a intensity of 0.04. The end CH3 has 3 proton. So, that corresponds to a value of intensity 0.04, whereas each repeating unit has one such A proton. This is the proton which is here. So, n number of repeating units will have n such protons. So, and this comes around 3.96. So, this is the signal for this n number of such protons which has intensity of 1. That means, if the number of repeat units is n, I have n such proton. So, this 1 corresponds to n proton, whereas this 0.04 corresponds to 3 protons which present at the end. So, I can write that integration of 1H proton or proton signal at the terminal methyl given by this. So, one proton have this intensity for this measurement, because 3 terminal proton has intensity of 0.04. So, if we divide 0.04 with 3, this is the value for one single proton. This is the intensity value of one proton. Hence, when we have one intensity which corresponds to 75 protons. Now, each repeating has one proton, which means N value is 75. That means the molecular weight corresponds to approximately this the repeating unit molecular weight of the repeating unit in this case is about 113. So, the molecular weight Mn in this case would be 113 multiplied by 75 plus the N group which is comes out approximately 8500. So, basically what we need exclusive group. Basically now we can quantify this number of what is the number of repeating unit if we know what is the ratio of N group with the repeating unit. Hence, we can find out the molecular weight, because we know the molecular weight of the repeating unit of the polymer. Okay, so, we will stop now, and in the next lecture I will talk about determination of molecular weight by dilute solution viscometry.